Now that we've talked more about atomic theory, we can come and talk about the iconic periodic table to some degree. Now, the actual arrangement of the elements in this form will make more sense when we talk about the atom again in chapters 6 through 9. But here we can discuss a few points. First, that the horizontal rows of the periodic table are known as periods, whereas the vertical columns are known as groups. Now, elements are grouped in these vertical columns based upon their similar properties, and this will again make more sense when we talk in chapters 6 through 9. However, the thing to pay attention here is that all of the elements are arranged in order of their increasing atomic number. Remember that atomic number is the number of protons. That's what defines that element as being that element. And as we go left to right across the periodic table, all of the elements are arranged in increasing order of atomic number. Additionally, elements on the left side of the periodic table are termed metals, with the exception of hydrogen. Hydrogen is the one exception that sits up here in the top left, but all of the other ones on the left side of the periodic table are known as metals, here in these first two columns, and then in this central block shown here. And then there is this step-like line that divides metals from non-metals. So everything in tan is a metal. Some of the elements shown here in purple that lie right along that line function as sort of metalloids. They have some metal behaviors, some metallic behaviors, and some non-metallic behaviors. We can talk in more detail in chapter 7 regarding those. But then finally, the elements on the right side of the periodic table are referred to as main group elements or non-metals. And that's all of the elements shown here in green. Now, with the periodic table, there are elements, as mentioned, that are grouped according to property, and each of these groupings has a name. And I'll go through the major ones. So on the left side of the column, excluding hydrogen, this first column is known as alkali metals. This is your lithium, sodium, potassium, rubidium, cesium, francium. These are your alkali metals. The second column is known as the alkaline earth metals. And then in the central block here, we don't talk too much about it. These are your traditional metals, so iron, nickel, copper, zinc, silver, and gold are in this main group of metals, or sometimes referred to as D block metals. We'll again talk in more detail later. But then on the right side of the table, there are also some common groupings that are important to know. So group 6A, or group 16, is known as the chalcogens. This is oxygen and sulfur primarily, although selenium and tellurium do come into play sometimes. And then the halogens are probably the most common group that you will hear of. This is group 17. And finally, the noble gases or rare gases are in group 18. And you may notice that there are also several different numberings of these groups. So there's one set of numbers that just goes left to right, 1 through 18. This is now the recommended numbering for the groups. And so if I refer to group 9, for example, what we're talking about is this one with cobalt, rhodium, and iridium. There is an older system, which is still fairly common, which splits the table into two parts, an A grouping and a B grouping. The A grouping includes the alkali metals and the alkaline earth metals, and then the main group elements or non-metals. And then the other traditional metals are grouped into a B group. It's important to know, or at least be aware of these different groupings, but the one we will primarily use is the preferred single grouping system that runs from 1 to 18. Now, all elements in nature, it's very rare to find elements in their actual elemental form. You will not be able to go out and find a single fluorine atom floating around, or a silicon atom by itself, or a hydrogen atom by itself. really the only atoms in nature that tend to exist as isolated atoms are the noble gases, so group 18. The noble gases do exist in nature primarily just as their individual isolated atoms. Some elements do exist as molecules, so that would be more than one of that same element combining together. And the most common form of this would be simply diatomic elements, where we have the molecules formed of two atoms of a single element. Now, in this case, the formulas are shown here for several diatomic elements. The 2 subscript indicates the number of atoms that are involved in that molecule. And we have 7 primary diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These are elements which in nature exist as diatomic molecules. These are important to know and be aware of, because when we talk about oxygen, the oxygen in the air, we're not talking about oxygen atoms. We're talking about the O2 molecule, because that is the form that oxygen exists in nature. As a result, it's important to know these 7 diatomic elements. And there's a little memory device that I use to help me keep track of them. And that is the name NOAA. And that would be N for nitrogen, O for oxygen, A for all of the halogens, so all of this group 17, and then H for hydrogen, so NOAA. You may notice that acetine here at the bottom is left off, but acetine is a radioactive element and does not exist in hardly any quantities in nature. So we leave it off of the memory device. But nitrogen, oxygen, all of the halogens, and hydrogen. Additionally, as we've sort of shown there with O2, H2, N2, that description of a molecule is known as a formula. And there are both molecular and empirical formulas and others as well, which we'll mention, for describing molecules. And we show here a cartoon depiction of several molecules. Underneath, you will see the molecular formula for each molecule. So CO2, that lists the carbon and both oxygen atoms, with the 2 symbolizing the number of oxygen atoms, or H2O2, with the subscripts indicating the number of that atom in the molecule. If the formula indicates the actual number of atoms present in a molecule, that is referred to as the molecular formula. There is also a very commonly used something known as the empirical formula. This is simply the smallest whole number ratio of elements that are present in a molecule. Now, in some cases, the empirical formula will be the same as the molecular formula, and in some cases, it will be different. So here, for example, if we look at the empirical formula, which I've listed underneath for several of these molecules, for carbon monoxide, the empirical formula and the molecular formula are the same, and same for CO2. But for ethylene, the empirical formula is CH2. That's the smallest whole number ratio of elements, of atoms, or elements here. And that is different from the molecular formula. Now you may wonder, why would we bother with the empirical formula rather than just listing the molecular formula at all times? There's 2 reasons. First, many compounds, which we'll talk about slightly later in this chapter, do not exist with a discrete molecular formula. Table salt, for example, ionic compound, sodium chloride, does not exist as a discrete molecular formula. It only exists in something that we can describe with an empirical formula. The second reason is that many of our analytical techniques for measuring the composition of a molecule, many of those techniques only give us the empirical formula. They don't give us the direct molecular formula. And so having an empirical formula is useful, and then we can determine a molecular formula from an empirical formula if we have additional information. Now, both of those 2 formulas, molecular and empirical, describe very simply the molecule, but they don't tell you how the atoms are connected. If I write CO2, I don't know that the carbon atom is in the middle and the oxygen atoms are on both sides. It could be the carbon atom on one side and then an oxygen in the middle and another oxygen. And that's where we come to something that's known as structural formulas. Structural formulas are something more like this, where we use lines for connecting. These lines are known as bonds, and we'll talk about those in more detail in Chapter 8. But this describes, these structural formulas represent how the individual atoms are actually connected in a molecule. And so here, for example, hydrogen peroxide, which our molecular formula would be H2O2, and with just the molecular formula and no other knowledge, we wouldn't know that it wasn't HHOO. But in reality, the structural formula shows us how the individual atoms are connected. In addition to structural formulas, there are further perspective formulas or ball and stick models or space filling models. All of these are just different descriptors for how molecules are connected together. Sometimes we can get three-dimensional perspective. So in this perspective drawing here, the solid lines are ones that are in the plane. If we have a plane of a board, those are in the plane. And then a wedge is a bond that's coming out towards us, which means that that atom is coming out towards us. Dash means that the atom that's connected is pointing back away from us. And we can sort of represent that in a ball and stick model as well, or space filling model.